Motorsport data usually looks like a wall of traces: speed, throttle, brake pressure, GPS positions, engine RPM, and a bunch of things. All useful, but it's a lot to read at once. Then there's this plot. At first, it looks like random dots have been thrown on a graph. There's no track map, there's no time axis, there's also no obvious corner number. But this strange looking cloud is one of the fastest ways to see how much grip the car utilized. This is called a GG plot, and once you know how to read it, it stops looking like noise and starts to feel more like a fingerprint of a lap. The outside boundary here tells us what the car might be capable of, the dots inside tells us what actually happened, and the gap between the two is where the engineering conversation begins. Today, we'll be looking at what the plot is, what is the physics behind it, then how the engineers use it for diagnosis through a simple hands-on simulation, and finally, how it all connects together in a full lap time simulation. A GG plot is an XY plot of accelerations. On the horizontal axis, we put lateral acceleration, which shows how hard the car is cornering left or right. On the vertical axis, we put longitudinal acceleration, which shows how hard the car is braking or accelerating. Every dot is one instant from the lap. If the dot is low on the graph, the car is braking. If it's higher up, the car is accelerating. If it moves left or right, the car is cornering. The important trick here is that we remove time. We are not asking what happened first, but rather we are asking what combinations of braking, acceleration, and cornering did the car actually use. The reason why ggplot matters is the tires. A tire can only generate a limited amount of force. If you use a lot of that force for braking, you have less left of it for cornering. If you use a lot of that for cornering, you have less left of it for accelerating out of the corner or braking for the next corner sequence. That is the basic idea behind the tire friction circle. This is also why the trail braking exists. A good driver does not always finish the braking and then start to turn in. They blend the release of the brake while steering in, trying to stay near the edge of the available grip instead of falling back into the middle of the plot. But the real GG plots are not perfect circles. Most cars can brake harder than they can accelerate. That's because braking can use all four of the tires and is helped by aerodynamic drag. Acceleration is limited by power, gearing, traction, drivetrain layout, which might be just one axle in most race cars, and the drag force. In addition to that, the load transfer also changes the available tire grip from front to rear and from left to right while turning. As we know, the tires are load sensitive, and if the car has downforce, the whole performance envelope changes its shape based on the speed, because the aerodynamic downforce is roughly the square of the velocity. That is why a 2D GG plot is good for the first look, but if you are dealing with a high downforce race car, a deeper version, which is the GGV plot, is a better representation. So now that we have understood what a GG plot is, let's actually go ahead and see how do we interpret it for the results that we have got. So I've already built a simulator using AI. We'll be using that to understand how to analyze the GG plot. It's not a full vehicle dynamics model. In this simulation, we have got some important controls for us to play with. So the simulator uses inputs like tire friction, vehicle mass. There's a simplified power drain model, a front to rear drive split. So if it's a front wheel drive or rear wheel drive car, there's only one axle which is doing all the driving. But if we put it in the middle, which means it's all wheel drives, you can see that the acceleration is a bit more in this case. One of the most important thing is the downforce. So as you can see, if I increase the downforce, the shape already increases in size, which means more load, giving us more grip on the tires. From these inputs, it generates two main things: a theoretical GG envelope. This shows what the model thinks that the car can actually achieve, and inside that there's a cloud of points. This is an example data that the AI has built. I have not imported any real data here. So even when this is not a full vehicle dynamics model, it gives us the basic idea. At vehicle level, we can think of this limit using a simplified friction ellipse. If the car is braking hard, it has less grip left for it to corner. If it's cornering hard, it has less grip left for it to brake or accelerate. Now, if I reduce the tire friction, the whole envelope shrinks, it becomes smaller, which represents the dry to wet idea. So if there are wet conditions, the car has less grip in every direction, so the limit moves inwards. And it could also mean the cold tires, a poor track surface, or maybe a different tire compound which is not producing as much grip. So the first question is, has the limit itself changed? So let's say if we keep all the car parameters as they are and just reduce the driver utilization, the ideal envelope stays where it is, but the point cloud moves inward. This means there's unused performance. Now, because we actually reduced the driver utilization, in real data, this could suggest hesitation, maybe conservative braking, delayed throttle application, lack of confidence, or simply a safety margin that the driver is driving with. This is why the center of the plot matters. If the middle is heavily filled, the car has spent time not accelerating, braking, or cornering hard enough. But sometimes this is normal. This could be a result of traffic, lift and coast, wet conditions, or just simply slow transition between subsequent corners. But compared to a faster reference lap, this could mean that the car had more grip available, but the driver could not use it properly. So the next thing that we look at is where the points are missing on the diagram. So let's start with the bottom of the plot, which represents the braking. The lower left and lower right regions show the braking and cornering at the same time, which is the trail braking region. If the points move confidently into these low corners, the driver is combining brake and steering on the corner entry. If those areas are empty, the driver is braking in the straight line, releasing the brake, and then turning afterwards, which can be safer, but it may leave lap time on the table. Now, let's look at the top of the plot, which is the acceleration region while cornering. And this is the corner exit. So if the engine power, traction, or throttle utilization is reduced, this region becomes weaker. If the envelope itself is low at the top, the car may be power limited or traction limited. If the envelope is available but the dots sit inside it, the driver may be waiting too long to apply the throttle during the exit, or may not trust the rear of the car on the exit, or the car could simply be unstable on the exit. Now let's bring in the downforce. So when the downforce increases, the plot does not grow equally everywhere because the aerodynamic load becomes more important at higher speeds. So the available grip increases more in fast corners rather than the slow corners. This is why the speed gradient is important here, because a simple 2D GG plot combines the slow hairpins, fast corners, mid-speed corners together in a simple 2D plot. Without any speed context, we may compare points that should not be compared. For example, at low speed, the car is mainly limited by mechanical grip, braking, traction, and the driver input. At high speed, the downforce can increase the available grip. So we should not only ask, are the points near the ideal edge of the envelope, but we should rather ask, are the points near the correct edge of the envelope, for which there's this 3D plot on the right which shows the 2D GG plots at different speed slices. So as you can see, as the speed increases, the downforce increases, which increases the envelope size, which means the available grip is more at higher speeds. So by isolating these speed bands, the simulator helps show whether the car is underusing the grip in slow corners, fast corners, or braking zones or exits. One more thing we can consider is the left and right balance. Sometimes the plot is stronger in one direction than the other and shows asymmetry. This sometimes is normal. The circuit may simply have more demanding corners in one direction than the other, but if the layout does not explain it, asymmetry can suggest setup imbalance, it can suggest uneven tire behavior. It could also point at sensor orientation issues, or maybe just the driver being more confident turning in one direction than the other. So it's not automatically a problem, but this is a clue. Finally, before trusting the plot, we must check the data, the wrong units, poor sensor mounting, vibrations, which could introduce noise in the data, could be incorrect orientation of the sensors, or could be the issues with the filters, which create misleading shapes. So for example, 1g acceleration is 9.81 meter per second square. So if the data mixes the g force and the meter per second square, the whole scale becomes wrong. For example, as you can see in this, the simulation is in meter per second square and the actual data is in the g force, which makes it looks very small compared to the ideal performance envelope from the simulation. So we can just adjust the units to match the both, so make sure that both of them are correctly compared. So the interpretation process is simple. Start with the ideal envelope, which tells us what the car can actually do. Then look at the point cloud, which is your lap data, which tells us what you actually did on the track. And then compare and see how much gap is between both, which could indicate unused performance. And then start looking at the plot itself. So if the lower corners are weak, look at the braking and trail braking. If the upper corners are weak, look at the throttle application, traction, or the exit stability of the vehicle. If one side is stronger than the other, check if the track layout explains it. If not, then look at your setup. And if the shape simply looks strange, check the data before blaming the car or the driver. See if there are any issues with the sensors and the data logging itself. So this is the value of the GG plot. It turns a lap into a visual map of the available grip. You can also use it in a full lap time simulation like this and compare other things alongside it. So for example, the driver inputs, which can literally show you what the driver did, and you can compare it with the GG plot to see if it matches and identify exactly where the performance is left on the table. If you want to try this lap time simulation, the link is in the description. So that's why this weird plot is one of the fastest ways to turn raw data into a fingerprint of the lap and a story about the car, driver, and the lap time. So stick around and let me know what else would you like me to cover next.